So in this clip, I will focus on Taylor's theorem, and Taylor's theorem says something about the error that we make by taking Taylor polynomials as approximations of functions. So what is this saying? So let's have a look at the nth order Taylor approximation at some point a for f, right? So we have a function and we're looking at the nth order Taylor approximation. So this means that for all kth order derivatives, we have equality with this the nth order Taylor approximations, at least when we take derivatives not too many times. So that means k is smaller equal than n, right? So we have that the Taylor approximations are tangent to the functions to order n. So how good are these approximations t of n for the function f around this value a? Well, let's have a graphical look at this. So here in this picture we see the function in red. We see the graph of the function fx is the ln of 1 plus x. Here we see in blue the linear one, the linear approximation, and in yellow we see the quadratic approximation, the t2, and here we see the cubic approximation of the function f, right? So t3. So we see that the closer we get to a, the more the smaller the error becomes. If we look at Taylor approximations, the further away from a we get, the larger the distance between the Taylor polynomials and the function itself. And also what we see here, and in this case we can see that the Taylor approximations for higher orders become more accurate to describe the function values themselves, right? So what we see is in this example that when n goes up, the higher the order of the Taylor polynomial, the better the approximations get. Okay, so there's two components: the order of the approximations and the distance that you are away from the point where you make those approximations. Okay, here again we have a similar example. So here on the left hand side we see the Taylor polynomials, higher order Taylor polynomials for the function, for the exponential function, and you see that we do it in a is 2, and you see that they are pretty much accurate around the point of 2, and the further away you are from the further x is away from 2, the larger the error that you would make if you use the Taylor approximations as approximate values for the function f. Something else that you can see is the higher the order of your Taylor polynomials, the better the approximations get. So again, we have two components. It is the distance from the point where you make those Taylor approximations and the order of the Taylor approximation. So here on the right hand side we see a similar picture, and here we look at the Taylor polynomials in 0, right? So again, it's good to realize that when we take Taylor approximations in 2, they are different from the Taylor approximations in 0. But for the Taylor approximations in 0, we see the same aspect. So here the blue line is the linear approximations, and we see that nearby a, the higher order Taylor approximations do fare better in terms of approximating the function values. And so there's again two components. The further away you are from the point where you define the Taylor polynomials, the higher the bigger the distance between the function values and approximate values, and the higher the order of the Taylor polynomials, the better the Taylor approximations. So these are the two basic intuitions for underlying Taylor's theorem. So now I will say something about the quality of Taylor approximations. I will come up with a theorem that I will call Taylor's theorem. And later on, we'll see some applications. So basically, I want to spend time on the remainder. What is the remainder term? Well, the remainder term with respect to the nth order Taylor approximation at some point x is a is just the difference of fx minus with the nth order Taylor approximation. So the Taylor approximation is getting better if the difference between fx and Tn of x is small. Okay, now Taylor's theorem. Well, it's a mouthful. It's not easy to read at first, but I will show you some components that I already highlighted. So Taylor's theorem, what is Taylor's theorem about? Well, let f of n be the nth order derivative. So we have f being n plus 1 times differentiable, and suppose these are continuous functions on the interval ax, right? So for all t in a and x, we see that this is a continuous derivative. Moreover, suppose that we have the n plus 1th derivative at t, and this exists for all t in the open interval in between a and x, right? So now we choose x larger than a, but we can also make a formulation of Taylor's theorem where x is smaller than a. It basically functions the same way. What Taylor's theorem now says is we can express the remainder in terms of the existence of a psi x. There's a psi x in between a and x such that the remainder of at x is given in terms of the n plus 1th derivative in this psi of x divided by n plus 1 factorial times x minus a to the power n plus 1. Yeah, so here you see these components, right? So here you already see the further away I'm from a, the higher this term will get, right? The higher this term will get, and this results basically the further I'm away from a, the worse, the higher the remainder of this, the remainder of the nth order Taylor approximations for f, and the closer we get and the higher the n, well, this n factorial, so if we have a modest behavior of the n plus 1th derivative, then the n plus 1 factorial will have some impact, right? So the higher the n, the better the Taylor approximation ultimately will get. So this is the first introduction of Taylor's theorem. Now we'll discuss some examples of Taylor's theorem.